Hello everyone, welcome. Today we are going to look at fatty acid nomenclature and triglyceride chemistry. And this is lecture 9 of the Introduction to Food Chemistry lecture series. In the previous class we understood what lipids are, we classified lipids and we gave the properties of lipids. And now we want to understand how is the naming of fatty acids done and what is the chemistry of triglycerides. Fatty acids are named using several systems that convey information about their carbon chain length, about the degree of saturation, and also the positions of any double bonds. And there are three primary nomenclature systems that are used in naming fatty acids. One, we have the delta nomenclature. And this one counts the carbon atoms starting from the carboxyl end. And the carboxyl end is designated as carbon 1. It specifies the total number of carbon atoms, the number of double bonds, and also the positions of these double bonds. And this can be indicated by the carbon number where each double bond starts. Let's take a scenario. We have an example of linoleic acid. Linoleic acid is denoted as 18:2 delta superscript 9 then 12. And what is the meaning of this? This is indicated as linoleic acid has 18 carbon atoms, but it has 2 double bonds, and each of these double bonds are occurring between carbon atoms 9 and 10, and also carbon atom 12 and 13. The carbon atom that begins the double bond, where the double bond is occurring, starting from, is the one we denote up. So that is why linoleic acid is denoted as 18:2 delta 9 12. The second naming is the omega nomenclature. This system counts the carbon atoms from the methyl end, known as the omega end, and it highlights the total number of carbon atoms, the number of the double bonds, and the position of the first double bond from the omega end. For example, let's take a scenario of alpha linolenic acid. It is represented as 18:3 bracket N-3. And this means that alpha linolenic acid has 18 carbon atoms and it also has 3 double bonds. But the first double bond is occurring at the third carbon from the methyl end. The third one is the common names, whereby we just have a certain common name for the fatty acids. Many fatty acids have traditional names that can often reflect their source or properties, and these names are widely used in both scientific and general contexts. For example, palmitic acid. This is this generic name. Palmitic acid has 16 carbon atoms and 0 double bonds, and it is a saturated fatty acid. Oleic acid has 18 carbon atoms, 1 double bond occurring at carbon atom number 9, and this is monounsaturated fatty acid. Linoleic acid has 18 carbon atoms, 2 double bonds, and the first is occurring at carbon number 6, and this is a polyunsaturated fatty acid. Let's go ahead and also look at the IUPAC nomenclature of fatty acids. The word IUPAC stands for the International Union of Pure and Applied Chemistry. And this union provides the systematic rules for naming fatty acids, and it ensures clarity and consistency in chemical communication. Fatty acids are aliphatic monocarboxylic acids, typically with unbranched chains of 4 to 28 carbon atoms, which may be saturated or unsaturated. So the saturated fatty acids have no double bonds, as we've already noted earlier, and the naming follows the alkene series with the suffix oic acid. For any fatty acids where you hear the last word as oic, that is a saturated acid. Oleic, linoleic, those are saturated fatty acids. For example, butanoic acid can commonly also be known as butyric acid. then hexadecanoic acid, also known as palmitic acid, and then we have the octadecanoic acid, commonly known as the stearic acid. The unsaturated fatty acids, for these, they have one or more double bonds, and this naming of IUPAC includes the position of the double bonds indicated by the lower numbered carbon atom involved in the bond. The configuration around each double bond is denoted as Z for the cis occurring at the same side and E for trans occurring at opposite sides. And this is following the Kern-Ingold pre-log priority rules. For example, we have 9Z, octadec9 enoic acid, and this is commonly known as oleic acid. It has 18 carbon atoms and one double bond occurring at carbon atom number 9. Then we have, and it is called Z because it is occurring as a cis on the same direction. Then we have 9E, octadec9 enoic acid. Carbon atoms 18, one double bond occurring at carbon atom number 9, but it is trans, commonly known as elydic acid. And then we also have 9Z, 12Z, octadeca9,12 dienoic acid. This is a fatty acid that has 18 carbon atoms, two double bonds, one occurring at carbon atom number 9, and it occurs in the same direction, cis, and then 12, carbon atom 12 also has a double bond occurring, and it is also cis in the same direction, and it's commonly known as linoleic acid. We also have the polyunsaturated fatty acids, also denoted as PUFAs. For fatty acids with multiple double bonds, the positions and configurations of all the double bonds are specified. Examples, we have 9Z, 12Z, 15Z, and it is called octadeca9,12,15 trienoic acid. This is a fatty acid that has 18 carbon atoms with 3 double bonds, and each of the double bonds is occurring, one at carbon 9, the second at carbon 12, and the third at carbon 15. And all of them are Z because they are cis configurations occurring in the same site. And this is called alpha-linolenic acid. That is the common name. We also have 5Z, 8Z, 11Z, and 14Z, ecosatetraenoic acid. This is a fatty acid that has 20 carbon atoms, and it has 4 double bonds. Each of these double bonds occurring, 1 at carbon 5, 2, carbon 8, 3, carbon 11, and 4, carbon 14. And they are Z because they are occurring on the same site. The common name here is arachidonic acid. So this is the nomenclature of fatty acids. Let's go ahead and also look at essential fatty acids. Essential fatty acids are called essential because they are needed in the body in a required amount, which can only be obtained from dietary sources. The body cannot synthesize these fatty acids. So the humans are unable to synthesize certain PUFAs because our bodies lack the necessary enzymes to introduce the double bonds beyond the 9th carbon atom from the carboxylic end. Humans are unable to synthesize certain polyunsaturated fatty acids because our bodies lack the necessary enzymes to introduce the double bonds beyond the 9th carbon atom from the carboxylic end of the fatty acid chain. And this enzymatic limitation simply means that we cannot produce double bonds at positions such as delta 12 or delta 15, which are very characteristics of the essential fatty acids. For example, the linoleic acid and the alpha-linolenic acid. And as a result of this, these fatty acids must be obtained from the diet. Then that's why they are called essential fatty acids. What is the biochemical basis of these essential fatty acids? The human body primarily possesses desaturase enzymes such as delta 9 desaturase, which can introduce a double bond at the 9th carbon position from the carboxyl end. However, our bodies lack delta 12 and delta 15 desaturase enzymes. These are enzymes necessary to introduce double bonds at the 12th and 15th carbon positions, respectively. But these enzymes can be present in plants, and this allows the plants to synthesize La, the linoleic acid, and ALA, the alpha-linolenic acid, which humans must then consume through the plant-based foods or oils. The metabolic implications of this: once ingested, the linoleic acid and the alpha-linolenic acid will serve as precursors for the synthesis of longer chain polyunsaturated fatty acids through a series of elongation and desaturation reactions. For example, the linoleic acid can be converted to arachidonic acid. Then the alpha-linolenic acid can be also converted into eicosapentaenoic acid. And this eicosapentaenoic acid can further be converted into docosahexaenoic acid. And what are the functions of essential fatty acids? One of the primary functions is cell membrane structure and function. They contribute to that. And then they also help in brain and eye development, especially in infants. And that's why young children, babies, newborn babies, are recommended to be supplemented with these essential fatty acids, or to consume food items that are rich in these fatty acids so that their brains and eye can develop. Production of eicosanoids. These are hormone-like substances that regulate inflammation, immunity, and blood clotting, and they're also important for cardiovascular health. Conversion pathways involved, as I already talked about. The alpha-linolenic acid can also be converted to eicosapentaenoic acid, which can further be converted into docosahexaenoic acid, important for brain and eye development. Then the linoleic acid can be converted to arachidonic acid. And we have to note that these conversions of alpha-linolenic acid to EPA and DHA is limited. So direct sources like fish oil are often recommended. Thank you.